All right, guys, we're going to go ahead and get started. To start, we'll talk a little bit about the format of the exam. It should be largely the same as the last exam. You should expect a true-false portion. You will probably see some multiple choice, but more free response I would expect than multiple choice problems. The multiple choice will probably be a tangent line problem, definitely be some related rate problems. You'll be tested on implicit differentiation, chain rule, product rule, quotient rule, power rule, all of the differentiation techniques that we have learned thus far. Be sure that you are submitting your exam as one PDF, as not to lose points unnecessarily. If you're still unclear on how to do that, because there were a couple people from the first exam who did not submit their exam in the correct format, if you're still unclear on how to do that, reach out to me and I'll walk you through it. Any questions regarding the exam and what to expect in terms of formatting? Okay. So there will be office hours this week, but that doesn't necessarily help you on this exam. Office hours will be on Thursday. Your exam will be tomorrow. I believe it's 7 o'clock. I'm not sure. I will be there as a proctor, and you will be able to ask questions, but they will be clarifying questions only. You won't be able to ask for any instruction. So today, if you have any questions, feel free to stop me as always. But today particularly, especially since there won't be another opportunity for you guys to ask questions after this recitation. For a screencast, let me do something really quickly. Okay. Alrighty. So we'll be going over Dr. Zalecki's review problems that he shared with you. I believe he shared them sometime last night. Included in those review problems were some true-false problems. I was going to present those during recitation, and then after realizing how much other material there was to cover, because Dr. Zalecki also did not include, or he didn't include any related rate problems in his review suggested problems. And so I thought it would be better to prioritize those problems, and that you guys could, and it's been brought to my attention that Dr. Zalecki will also be posting the answers to the true-false as well as the rest of the problems. But the true-false are a little bit easier to fill in the blanks on. If you have any specific questions about those, feel free to reach out to me, but I will not be addressing the true-falses directly since Dr. Zalecki will be releasing the answers to those. So we'll start with the differentiation problems. So you will have problems that will ask you that are specifically just differentiation, but I would expect the brunt of the exam to be more of the story problem direction. I got a question during first recitation as to whether or not there would be graphing problems. You will see some graphs on your exam, I would expect, but it's not going to be like with last exam, how there were specific types of problems that you had to maybe go from the first derivative to the second derivative. What I would expect as far as graphing goes on this exam is that you would be asked to do calculus, do written calculus, and then say they want you to plug in a derivative, and maybe they'll have you refer to the graph to identify what the derivative is at that point. But that at this point is just a little bit, it's a kind of a background skill considering we've done some more complicated graphing problems. So I wouldn't necessarily go out of your way to study graphing problems. I would definitely be focusing on differentiation. And once you've got differentiation down, and again, that's product rule, quotient rule, power rule, chain rule, that we have built upon to learn implicit differentiation, and following implicit differentiation are related rate problems. So the related rate problems, if you're good at those, that means you've got all of the skills basically down pat. And then I'll also say that there will most likely be a tangent line problem. So be familiar with those, but that's nothing new. I believe we had one of those on the first exam as well. So starting with these differentiation problems, the textbook just says calculate y prime. And I point that out because we will do an implicit differentiation problem. And so just bear in mind that the only instruction you're given for these problems is to calculate y prime, to calculate the first derivative. So for this one, off the bat, we can see that there are going to be two aspects to its derivative. We've got the outermost aspect, which is going to be a power rule operation. And then again, on the inside, we will have another power rule operation, but we will start from the outside in. So, and in doing that, we will keep the inside the same. So that'll look like dropping the 4, reducing to 1/3, keeping all of this the same on the inside for the first term. So there's a cube right there. And then for the second term, we will multiply by the derivative of the inside. This is classic chain rule at this point. I would hope that you guys would get full points on a question like this on the exam, because like I said, this is a skill that we have built upon to work on higher level problems like our related rates and implicit differentiation. So you should definitely have a handle on a problem like this. The main thing to keep in mind is that you address these chain rule problems from the outside in. And so if you see that there's a function, so we could call u, we could say that u is equal to x squared plus x cubed. This is then u to the fourth. So you have to do the derivative of u to the fourth, and then bear in mind that u is a function itself that has its own rate of change that will affect the greater rate of change y prime. Any questions on chain rule or power rule for this one? Okay. 15, another chain rule problem. Well, so this problem, you could choose to go about it as a power rule or as a quotient rule, or a product rule, I should say. So what I tend to do is I tend to take things from the denominator if they're simple enough and do a power manipulation such that I can do the product rule. I find the product rule to be simpler in terms of how many terms I'm going to write down. If you don't want to cloud your mind and think about these other steps, you could just go straight to doing the quotient rule. That would be fine too, but you're still going to have to do this power manipulation in order to identify that this is actually x to the 1/2 in the denominator. And so when we bring it up to the numerator, it becomes x to the -1/2. And then we have two multiplying functions that we can do the product rule on. So it'll be the derivative of the first, power rule 2x minus 1 is the constant in front of x, times the second, plus the first times the derivative of the second. There are a handful of students in every semester that I've taught who will make silly mistakes when it comes to subtracting these powers. And if you found that you were one of those students who is doing the calculus fine and you understand the greater concept, but maybe you're getting a little overwhelmed and wrapped up in the larger concepts and you're making little mistakes like this, I would definitely recommend that you draw an arrow off to the side and just write out the simple math. It might feel a little tedious, but if it'll earn you points or save you from losing points based off of silly mistakes, I would definitely recommend doing that. For the next one, we have another example of the product rule. So we have x squared as our first function, and then sine of pi x. So again, with the product rule, we'll do the derivative of the first times the second plus the first times the derivative of the second. The only thing that I would say is cause for confusion here is just bearing in mind that pi is a constant. And so if you're struggling with this concept so technically this is a double chain rule, or not, I shouldn't say double, but this is a chain rule problem. So the derivative of sine pi x itself, what I'm trying to say is sine of x, you'll take that derivative. And then pi x is a function within. So if sine of x is the outermost aspect of the function and pi of x is the innermost, you'll take the outermost aspect of the derivative, which would be cosine of pi x, keeping pi x the same on the inside. And then you'll isolate and you'll think about what's inside the parentheses, even though the parentheses are not written. And you'll bear in mind that this is basically a 3.14, and that 3.14x is going to have the rate of change of 3.14. And so you can either choose to multiply it in sequence if conceptually that's a better representation for you, or you can pop that as a constant out front. But that's where this aspect of the derivative comes from. Any questions so far? Cool. All right. Number 21. So this one I rewrote, and I was a little bit redundant with my double parentheses, but I just wanted to make it clear because if you guys remember from one of our past recitations when we were first introducing differentiation and trig, I made a note about how sometimes say it was tangent squared. Sometimes you will see, this is driving me nuts. Sometimes you'll see the squared right there. And sometimes the square will be applied to the entire, like from on the outside, maybe it'll be tangent in parentheses and then it's squared. And I wanted you guys to be aware of the fact that those two, they meant the same thing. This is different because the square root is being applied only to what's inside the tangent, what's inside the parentheses. And that's why I did these double parentheses. If you can logic that and conceptualize that in your brain without writing it out like that necessarily, then that's fine too. You aren't expected to write an intermediate step like this, but I did. And so what it's going to look like is we're going to take the outermost aspect of the derivative, the outermost being the tangent, and then we'll keep everything on the inside the same. So derivative of tangent is secant squared. keeping this the same. And then we'll multiply by the derivative of the inside, which is going to have two parts. So we're going to first address the power rule part, and then we see that there's another variable in there, and that negative x is another function whose rate of change is going to contribute to the larger rate of change y prime for this question. And so we have the outermost aspect, the first chain of the chain rule link, and then we multiply by the derivative of the inside, which is going to be 1/2, keeping everything on the inside the same, to the negative 1/2 because we've reduced by 1. And then we multiply by -1. I see what I did here. Then we multiply by -1 to account for the derivative of that negative x on the inside of our parentheses here. All right, so now we're getting into implicit differentiation. At this point, actually, let me take a step back and let's talk really quick about the trig problems. Just want to remind you guys that as far as trig derivatives go, you need to be familiar with the derivatives of tangent, sine, and cosine, and of their inverse counterparts. And then I believe you also need to know the derivative of secant, not secant squared. That's the derivative of tangent, but you need to know the derivative of secant. Well, yep, that would fall into, yep. And then on top of that, you guys need to be familiar with the unit circle. And we'll do a problem later. It'll be a tangent line problem, I believe. We'll do a problem later on that'll give you a little bit more direction as to what you're expected to do with the unit circle. But the unit circle is something that we're going to use and stick with for the rest of the semester. And so aside from memorizing those derivatives, you need to know the unit circle and then any identities that might have popped up thus far. So that maybe that'll look like L'Hopital's rule, which is the limit as x tends to 0 of sine of ax over ax, that will be equal to 1. That is one example of a trig identity that we've used so far. And so I would recommend looking back to the first recitation of this unit. Off the top of my head, I can't remember if that was recitation 4 or what, but I would take a look back at those problems that we did at the beginning of the unit, because that's when we did most of the legwork as far as trig identities goes. So you need to know those derivatives that I mentioned, and then you need to know the unit circle, and then you need to know any trig identities that we've used. And I believe Dr. Zalecki or I emailed you a list of trig identities that at some point throughout this unit that may be used. So moving on to this next problem. The reason I pointed out that it says calculate y prime is because all of these, the pretty classic differentiation, we're used to seeing y on the left and then some variation of a variable on the right-hand side. And then they throw in this implicit differentiation problem, and they don't explicitly say use implicit differentiation. Sometimes I've seen that professors will present it as use implicit differentiation. They'll write that in the question and direct you in that way. This is an example of a time where they do not, or this particular problem does not introduce it as implicit differentiation. So what I'm saying is be able to recognize by this mix of variables that this is an implicit differentiation problem, that you're going to do this differently than classic differentiation. Even if he doesn't say use implicit differentiation, Dr. Zalecki, on the exam, you should be able to identify by the fact that there are mixed x's and y's on one side of the equation. And also bear in mind that this could be equal to 0 or it could be equal to 1. It doesn't necessarily have to have x's and y's on both sides of the equal sign, but be able to identify that this is implicit differentiation without being told explicitly that you need to use implicit differentiation to find this derivative. That being said, you will be told to find a derivative. He's not just going to throw an equation up there and have you guess how to finish the problem. But if he says find y prime and you're given this mix of variables, then you should infer that it's going to be an implicit differentiation problem. And, excuse me. And so the way that that's going to look is, again, we're going to treat x as a function, or we're going to treat x as a variable, but then we're also going to treat y as a function and a variable. And the way that those are going to interact is that we're going to use power rule, product rule in the same way we would if we were just using two functions. So derivative of the first, we treat it as a variable times the second plus the first times the derivative of the second. First, the derivative as though it were a variable. Then by the chain rule, the derivative, because we know that y is actually a function. And that serves to help us. Well, I mean, this is the only goal here is to find y prime. And so we know we're on the right track if we have a y prime or 2 or 3 in there, because what we're trying to find is y prime. And we know that we will eventually isolate that y prime variable, or that y prime, in order to figure out what the derivative is. So again, we have the derivative of the first times the second plus the first times the derivative of the second as a variable, and then by the chain rule as a function. And then we'll do the same thing again for this second term, this x squared y. Derivative of the first times the second plus the first times the derivative of the second, which will be equal to derivative of x, which is 1, plus the derivative of 3y prime. So if this doesn't click to you, so basically the 3y prime term is what I'm addressing now. The derivative of y is y prime. If there's a constant out front, you don't get rid of the constant. It's just 3y prime. If that doesn't click for you and that doesn't make sense and you need a little bit more background, you could go about this using the product rule. You could treat 3 as though it were a function. Well, I mean, we use the product rule between variables. So like, for example, if we had sine of x times x squared, we would use the product rule for that. You could say that this is sine of x, this is x squared, but then what you'll find is that 3 is going to have a rate of change of 0, and so it's going to cancel that term out. So if this, I've noticed that some students, they don't know, for whatever reason, this is so simple and there's so little explanation behind it that some people don't have a grasp on it. And so if you're one of those people, maybe just go about it as though it were a product rule problem, and maybe it'll sink in. So moving on, next thing we're going to do is we're going to consolidate all of our terms that contain a y prime on one side of the equal sign and all of our terms that do not on the other side. And we typically see that as the y prime terms being on the left-hand side, because we're used to seeing y and y prime on the left-hand side of the equal sign. So we've got all of our y prime terms on one side and all of our non-y prime terms on the other. And then the next step will be to factor. So we're going to factor that y prime out of every single term. And I failed to write the final step, but when we do this problem down here, I do write out the final step. But basically what's going to happen here is we're going to divide everything on the right-hand side by everything inside these parentheses, and it'll be y prime is equal to this fraction where this is on top and this is on bottom. And so to reiterate, with these implicit differentiation problems, and with many of the problems that we do in this course, there will be a breakdown of these problems that'll be pretty much the same from time to time, or from problem to problem. And so the breakdown is basically one step of calculus. You do the implicit differentiation. You're going to use the product rule and the quotient rule and the chain rule and the power rule if you need to. But it's going to be just one step of calculus. From there, you're going to get all the y primes on one side, all the non-y prime terms on the other, factor out, and then more likely than not, you're going to divide in order to get y prime by itself. So really, it's one step of calculus, and then from then on, it's algebra to isolate the y prime term. Any questions on implicit differentiation so far? We'll do 1 or 2 more. Okay. All right, so addressing this sine of xy term first. We're going to start with the outermost aspect, so it's going to first be a trig derivative, but then we also know that by the chain rule, we're going to have to find the derivative of what's on the inside, and within the chain rule, we're going to have to use the product rule, and then the chain rule again in order to do implicit differentiation. So there's a lot of steps for just this one little piece of the derivative, but once you break through it, it's not that bad. So addressing the outermost aspect, we're going to take the derivative of sine, which is going to be cosine, and we're going to keep what's inside the parentheses the same. So the first term is going to be cosine of xy. Now that we've done the outermost aspect, the first link in the chain for chain rule, we're going to do the innermost, which is going to be product rule, derivative of the first times the second plus the first times the derivative of the second. And then that will be equal to derivative of 2x is 2. Derivative of negative y is negative y prime. So from there, same as we did with the problem before, we are going to isolate all of the terms containing y prime to the left side of the equal sign. Again, you could do it on the right-hand side, but this is what people seem to be most comfortable with. This is standard convention. And so we get all y prime terms. Well, actually, I misspoke. So this problem is a little bit unique in that you won't be able to isolate the y prime term unless you FOIL this out here and you distribute the cosine of xy. Otherwise, your options are really to divide by cosine of xy on both sides, but then you end up with this free y prime term because it's no longer being multiplied by cosine of xy. However, this y prime term will then be divided by cosine of xy, and it'll be locked into that fraction, so to speak. And so in order to get the y prime, both y primes, get them free so that we can isolate them, we're going to distribute this out so that we get y cosine of xy plus xy prime cosine of xy equal to 2x minus y prime. So then we can just subtract this term over, and then afterwards we can just, once we subtract the y prime over as well. So I'm getting ahead of myself here, but to back up, we did the calculus step, we did the implicit differentiation. From there, we realized we were going to have to distribute this cosine in order to get the y prime by itself. And so once we distributed the cosine, now we are going to get all the y prime terms on the left-hand side. So we subtracted this negative y prime over here, and we kept this y prime term here. Then this term will get taken over. It should be subtracted also, but it does not. Negative in this case, or it should be negative, but I made a mistake. And so then we have negative y cosine of xy plus 2x. From there, we're going to factor out a y prime. Keep everything on the right-hand side the same. And then finally, we will divide by the non-y prime term. And that's our final answer. And this step here is the one that was missing from above, if that wasn't clear before. Okay, any questions on this one? Before we move on, we're going to do a tangent line problem next. Oh wait, no, we are not. But we are going to move on from implicit differentiation. Okay. I just kind of want to, can somebody say something so I know that you guys can ask questions? I've got a little bit of stress from the, okay, good. It's this persistent fear that you guys can't ask questions, and today is the very last day, is the only day that is the most important that you guys should be able to ask questions, is on review day. So good. All right. If f of t is equal to square root of 4t plus 1, find f double prime of 2. So first thing I did was I reorganized it. So I did a fractional power manipulation in order to get this into a form so that I can do the power rule on it. At this point, this should be pretty obvious. I tend to reiterate myself on this, but that's what we're doing. So we're being asked to find f double prime, the second derivative. And there's really nothing special about finding the second derivative. Implicit differentiation is a little bit different, but I have yet to see an example in this semester where Dr. Zlecki asks you to find the second derivative as far as implicit differentiation goes. So I wouldn't worry about that. But as far as classic differentiation goes, there's nothing special or new about it. You just do it twice. Sorry. And so we're going to take the derivative first by the power rule. We're going to address the outermost aspect. So we get 1/2 4t plus 1 to the negative 1/2. Then we'll multiply by the derivative on the inside. And then I simplified that because I know that I'm going to be using it again in another step. So there were some questions during first recitation about when you should and when you shouldn't be simplifying after at the end of a problem. And I know we've talked about this a couple times, but since it's before exam time, I'll go ahead and say it again. If the problem is asking, say for example, we were looking at this problem here. They asked you to find y prime. Okay, good. You found y prime. I would not waste my time, and I would not risk making mistakes by simplifying this or trying to combine like terms or anything like that. There are really only two situations in which I would say that you need to simplify further. One being when you're doing a trig problem. And like I said, we will get to a trig problem. But if you're given a specific x value, say pi over 2, and you have the ability to plug in, then you should plug in, because part of the concept of working with these trig problems is that we want you to understand the unit circle and be able to apply it. And so if you're doing a trig problem and you are given a coordinate or an x value that will allow you to plug in, then you should simplify to the simplest form of the answer. Another time when you should be simplifying maybe a little bit more than you would ordinarily, would be a problem like this where there are intermediate steps. And the reason for that is you're going to need to use your simplified version of the equation in order to expound on that work and find the final answer that's being asked of you. You could still do it like this if you want to. That's technically still true. You don't have to simplify it, but it just serves to make things more confusing. And so again, to try and avoid making mistakes, if it's, and then it becomes a bit of a balancing act. But in this case where it's just multiplying 4 by 1/2, simplify it and then go from there. And so going from there, we're going to take the derivative of again. And so it's going to be the exact same thing as last time. We're going to drop the power, maintain that constant out front. So we have -1/2 times 2 times everything on the inside the same. And then we've reduced that 1/2 power by 1. And again, we're going to multiply by the derivative of the inside. And constants, just to reiterate, I know I've said this a million times, constants have a derivative of 0. And so this, if you were asked just to find f double prime of t, I'd say that this is a perfectly fine answer. You don't have to simplify it. However, the question is asking you to find f double prime of 2. So there's kind of 2 intermediate steps to this problem. So we're doing some more simplifying than I would normally say that you have to do. And so we simplify that to be -4 times 4t plus 1 to the -3/2. So then we can plug in that 2 value. And when we plug in 2, we find that this in the middle here in the parentheses simplifies to 9, keeping that -4 constant out front. And now we'll talk a little bit about how you break down these powers. So in general, it's always smart to start with, when it comes to fractional powers, it's always smart to start with what is in the denominator. So if we look back up at here, a square root, that makes something smaller. And so we have a fractional power. The fractional power makes something smaller. So what's in the denominator here is going to make it smaller. You're going to take the square root. If it were a 3 in the denominator, you'd be taking the cube root. But in this case, since we're taking the square root, we know that the square root of 9 is just 3. And so we still have that -4, and it becomes 3 to the -3rd because we have then taken the square root and that 1/2 power goes away. Now we can address the cubed. It would be more difficult if we were to try and cube 9 and then take the square root of that. It's always simpler to go smaller and then get bigger. And so now when we cube 3 to the 3rd is 27, but we still have that negative sign. And so we pop 27 in the denominator. Any questions on this one? Just a few steps to this one. So any questions at all? Okay. You guys aren't very talkative today. Hopefully that means you guys feel prepared. Alrighty, number 47, find the equation of the tangent line at the point y, or at the point pi over 6, 1 for the equation y equals 4 sine squared x. So this is a tangent line problem. Obviously it says it in the question, but off the bat, like many of the other problems that we do in this class, you can kind of guess what the steps are going to, or you know what the steps are going to be because they're pretty much formulaic. Every time that you do them, it's going to be roughly the same, unless, for example, how up here we had to do some distributing, unless there's some sort of like finicky algebra thing that you maybe didn't foresee. In general, you can guess how these problems, or you can picture how these problems are going to go before you even start. So we know that finding the tangent line, in terms of the concept of what a tangent line is, say we've got this, we're going to call this f of x is equal to -x squared. Say I want to find the derivative at x is equal to -1, or x is equal to 1. So the theory or the concept behind this tangent line here is that since it's touching, what a tangent line does is it touches at one point on the outside of the curve. And so that right there is supposed to be representative of an estimation of the instantaneous slope. And so that's what they're asking you to find, an equation for the instantaneous slope. So it's not sufficient just to find what the rate of change of that would be, because if say you've got an equation, say you've got a graph and all you know is that its rate of change is 1, that would be y equals x. Well, if it's y equals x minus 1, that's going to look different than y equals x plus 1 or whatever it is. And so we have to find the rate of change and we have to find its specific intercept in order to represent that rate of change more accurately. And so we'll get to the calculus here in a second, but since I'm talking about intercepts and things like that and the specificity of a graph as it relates to its derivative, when we're talking about which equation to use, there's y equals mx plus b. That's what we all learned when we were in high school. I always use point slope form, and that's because you can just plug these right in. So pi over 6 would go straight into x1, 1 would go straight into y1, and then once you find the derivative y prime, which is equal to m, you would plug that right in here too. Whereas with y equals mx plus b, you're combining the y1 and the x1 term in order to find out what b is. That a waste your time, gives you more work, and B, gives you more of a chance to make mistakes. And so much like with oversimplifying, I would recommend that you don't do that. You use this equation. Don't use the y equals mx plus b unless that's what you're super comfortable with and that's how you've learned it. Then I wouldn't recommend that you change at this point. But this one is generally simpler. It cuts out work and people tend to like it better. I like it better. So we're going to go back to the problem here, and we know that the legwork here really lies in taking the derivative, because beyond that, we just have to plug in. Specifically with this problem, we're going to have to plug in and find what the derivative is. So there's going to be a little bit of legwork when it comes to trig, but for general tangent line problems, say it wasn't a trig problem, after you take the derivative, you've done most of the work. And so to take this derivative, we're going to start with the outermost aspect, which is going to be the square on the sine function. So we're first going to address the power rule part of the derivative. And if this square here in the middle of sine is throwing you off a little bit, you can visualize it as sine in parentheses, sine of x in parentheses, and then the square on the outside, because those two are equivalent statements. And so when we do that, we're going to drop the 2. So we keep the 4, drop the 2, becomes 2 sine x. Then we multiply by the trig derivative, which is cosine of x. Derivative of sine x is cosine of x, which I then simplified because it's an intermediate step to 8 sine of x cosine of x, just for sake of simplicity. And then since I need to find the specific, so I've just found the general formula for the derivative of this function, and I can plug in any x value and find any specific derivative. And the specific derivative I'm being asked to find is pi over 6. So when I plug that in, I get 8 sine of pi over 6 cosine of pi over 6. And now I've got to refer to the unit circle in order to figure out what these specific values are. And so I'll remind you guys that sine correlates to y, to height. Cosine correlates to x. And since we're doing pi over 6, we need to think about this short. So there's the 45, 45, 90 triangle. Pi over 4 right here would be a 45, 45, 90, which would have equal legs, and then its hypotenuse would be 1. But we are concerned with pi over 6, which is the 30, 60, 90 special right triangle, with also with a hypotenuse of 1. And so it's going to have a height of 1/2 and a width of square root 3 over 2. These are values that you should have memorized, and you should have them memorized for pi over 6, for pi over 4, for pi over 3, and then for pi over 2. And then from then on, it's just reflecting over the different axes. All the values are the same. You really only have 2 triangles to memorize, the 45, 45, 90, and then the 30, 60, 90. And then you just have to recognize that the 30, 60, 90 is either going to be laid on the long side or it's going to be put up straight, and that they're the same values. It's just kind of flipped. So that being said, we've just determined that this is going to be our sine because it's a height, and this is going to be our cosine because it's the width. So we get 8 times 1/2 times square root 3 over 2, which then simplifies to 2 square root 3, which is going to be our m. That's our y prime, our specific m, at the instant we're being asked to evaluate. And so we can just plug in all the info that we have into this equation now. We plug in the 1 for y1, our derivative goes here, and then pi over 6 for x1. Any questions on this one?
Do you want us to take that equation and put it into the y equals mx plus b, or are we good to leave it as a y minus y1?
I would recommend that you do not put it in y equals mx plus b.
Okay, thank you.
This is perfectly good. All right, so we're going to crank through these pretty quickly because we've pretty much exercised all of these concepts, and we are getting a little bit short on time, shorter than I would like to. So we're probably going to run a few minutes over. That being said, if you guys have got to get going, that's totally fine with me. But I will probably end up running a couple minutes over in order to explain the related rates as well as I'd like to. So as far as these go, we're just going to be talking about product rule and compound functions and things. So we have derivative of the first, 2x times the second, plus the first times the derivative of the second. The only thing to note about these problems is that so x squared is a function, so is g of x. And we're just not going to tell you what g of x is, and we want you to conceptualize what these derivatives would look like. And so it would just be a product rule problem, derivative of the first times the second plus the first times the derivative of the second. So now with this one, g of x squared, imagine it was sine of x squared. First, we would address the square aspect of the function. We would address the power rule. And then from there, so we would drop the 2, reduce it to 1. From there, we've got to account for what the derivative on the inside is. So this is the power rule aspect of the derivative, and then this is the chain rule aspect of the derivative. So then here we've got a compound function, g of x. So we often, like I've seen a couple people get a little confused with the FOG. That's what this is. And so and again, this is just a chain rule problem. So it's going to be the derivative of the outside, keep the inside the same, times the derivative of the inside. And then finally, this is exactly the same, only in this time it's not g of x, it's g of sine of x. Derivative of the outside, keep the inside the same. And then this is a mistake, that should be cosine of x. And then multiply by the derivative of the inside. Okay, we are gonna get going on our related rate problems. Excuse me. So to start, the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, at what rate is the area increasing? So we've got a rectangle. I realized during first recitation that this probably would have been better represented if I had written drawn the rectangle up and down. But either way, I decided to assign this length as x and this length as y. So this is going to be, so x is going to be the 8 centimeter length. It's going to be the length, quote unquote. And then y is going to be the width. You could do L and W, whatever. I chose to use x and y. So we're told that x is increasing at a rate of 8 centimeters per second. We're also told that y is increasing at a rate of 3 centimeters per second. We are also given the specific values at the instant that we're asked to evaluate them. And so what is dA dt? That's what we're asked. When the length is at 20 centimeters and the width is 10 centimeters, at what rate is the area increasing? So we need to find dA dt. And what equation are we going to use to wrap in all of this information? The area of a rectangle, x times y. I don't think we really need to get into why I chose this equation. And so we just differentiate the area equation. dA dt is going to be the derivative of the first times the second plus the first times the derivative of the second. These are both functions. One, it's so like when we do implicit differentiation, this is technically still using implicit differentiation, but when we do implicit differentiation, we're used to seeing, I'll say we treat x as a variable, and then we treat y as a variable and as a function. That's not necessarily correct math terminology, but in my attempt to break it down into English for you and help you guys understand what's going on, that's how we treat implicit differentiation. For these problems, they're equals. There is no variable and then variable function in the same sense that I presented it to you guys for implicit differentiation. These two are both changing, and they're changing, I don't want to say independently, but for implicit differentiation, more often than not, it's dy dx. So y is changing with respect to x. In this case, that relationship goes both ways. And so we get dx dt times y plus x times dy dt. So there, basically what I'm saying is that there's no, you don't have to think about which one is changing with respect to the other. They're both functions. And so you're going to treat them exactly the same as you would say if you were doing x squared times sine of x, just regular product rule. And so from there, we have all of the values that we need to plug in. So we're given dx dt, dy dt, x and y. And when I plug those in and simplify, I get 140 centimeters squared per second. Any questions on this one? Okay. This next one I am going to go through very quickly because after doing it the first time, I realized that this answer down here is quite familiar and that I had presented this problem to you guys during the first recitation where I introduced related rates. And so we will go through this really quickly because the setup it's valuable to hear it walked through. But I'm going to quickly go from this one to the next because the next two are the ones that I want to put the most emphasis on, and we are down to 10 minutes of recitation time. And so the radius of the sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? So we're told that the radius of the sphere, dr dt is equal to 4 millimeters per second. I have named my, on my diagram over here, I've called this r for obvious reasons. We're told that the diameter is 80 millimeters. So that means we're gonna have to do some sort of a little conversion. That requires you to know that the diameter is 2 times the length of the radius. And the reason I'm gonna do this, I'm gonna simplify this in terms of r, is because I know that the volume equation, because I need to find dv dt, of a sphere is based off of radii. It's based off of the variable r. And so I need to get the information that is given to me in terms of diameter into a workable form, which in this case will be radius. And so from the volume equation, we're just going to differentiate. We do the power rule. We drop this 3 down front, reduce this to 2. And since the radius is changing, it has its own independent rate of change that's going to affect the greater rate of change times dr dt. Now I've got all the info that I need to just plug in. And so that's what I do. Plug in all these values, simplify, and then I get this familiar 25,600 millimeters cubed per second. So again, if you have any questions on that one, you can email me separately, but look back at the old recitation recording and I will go a little bit more into depth on that one. So number 15, a street light is mounted at the top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second on a straight path. How fast is the tip of the shadow moving when he is 40 feet away from the pole? These examples come from section 2.8. If you are wondering, this does not come from the chapter 2 review. So if you're looking for these problems, this is section 2.8. So this one is probably the most important example of drawing a diagram, or it's the example where that is most important to have drawn a diagram. And the reason for that is we're given all this information, and without drawing the diagram, it might not be easy to sort through that information in your mind and visualize that this is going to be a similar triangles situation. So we often have to do a conversion when we do our related rate problems. Our conversion in this case is going to be between similar triangles. Up here, our conversion, and there doesn't necessarily have to be just one, but our conversion here was putting what was given to us in terms of D into terms of R so that we could use it with our volume equation. So when we draw our diagram, we have to keep in mind that this person's 6 feet tall, but his shadow is going to go further. We know that he's 40 feet away from the pole, and his shadow is going to go further to the left. So these diagrams are helpful in getting a bearing on the problem, what's being asked of you. So this distance here is increasing. The information that we're given, we are asked to find how fast the tip of the shadow is moving when he is 40 feet away from the pole. This is kind of tricky to come up with on your own, I will admit. So that's why I went from this diagram here, and I know that the distance from the guy to the post to the pole is 40, but 40 isn't it's at least whatever this value that wherever the tip of the shadow is, it's going to be more than 40. I know that because he's moving away from the 40. And his shadow is going to be by nature of where the light is casted away from where he is at 40 feet away. And so when I draw out my special right triangle, or when I draw out my similar triangles, I visualize X as being this 40, but then I also have to take into account the length of his shadow. And so the whole length of this triangle is going to be X plus Y. And so if we regard the whole length of this triangle as X plus Y, then the very end of it is going to be the tip of the shadow. And so X plus Y, if the tip of the shadow is increasing, it's moving away, ddt of X plus Y is going to give us the rate of change, the speed at which the tip of the shadow is moving when he is 40 feet away from the pole. Before I get into the rest of the calculus, is there any questions on that? You can just say, can you explain that again? Because I get that this is a little bit convoluted. And if not, I'll keep going.
Can you explain that again?
Okay, yeah, no problem. I remember when I was learning this for the first time, and it was kind of hard for me to wrap my brain around. I might end up just kind of repeating myself, but I don't think that that's a bad thing in this case. So let's go through the problem again. Street light is mounted at the top of a 15-foot tall pole. So we got the lamp down, that's easy. A man is 6 feet tall. So that is represented here on this diagram. So we've got 15 and 16. He is moving at a speed of 5 feet per second on a straight path away. So we've got dx dt, because I've determined that this is x. We've got dx dt equal to 5 feet per second. We are also so we're asked to find how fast the tip of the shadow is moving when he's 40 feet away from the pole. So we aren't evaluating, he's not stopping at 40 feet. He's not standing still at 40 feet. We're asked how fast is the tip of the shadow moving at the same time that he's moving 5 feet away, or 5 feet per second away from this post, from this pole. And the instant at which we're being asked to evaluate that is when we're 40 feet away. So he's still moving, And the shadow is, so when you get further and further away from a light, the shadows get less and less clear, right? So the rate of change is going to change as well. And so what's important about all this and drawing the diagram is being able to break this down into these triangles. And the reason for that is because we know what his X value is. What we don't know is how long his shadow is. And that's not going to be a constant value. It's going to be longer and shorter at some points relative to how far away he is from the light. And so since we are regarding this as X plus Y as this larger value, the reason, or this larger value is not the right word, we're calling this whole leg of the triangle X plus Y because we know that part of it is the distance from him to the post and part of it is the distance from him to the tip of his shadow. And so we're calling it X plus Y, and that wraps into the triangles in that we're going to do this special, or by similar triangles, we're going to get this X plus Y in terms of only X. Because one thing that we know is that we don't know anything about Y prime. We're only told dx dt. And so if we are going to break this down in terms of X and Y, which they've already done that for us, the way they presented the problem is that he's 40 feet away. Now you need to figure out how far away or how fast the tip of the shadow is moving. And so when we're talking about how far away the tip of the shadow is, we're going to call that extra distance Y. So then the whole distance in terms of how fast the tip is moving from the pole, we're going to call that X plus Y. To find that rate of change, how fast the tip is moving, we're going to find ddt of X plus Y. However, we don't have information on how Y is changing. And so we have to get X plus Y in terms of X, in the same way that we had to get the diameter in terms of radius, because that's how the volume equation was given to us. And so we're going to do this by similar triangles, we know. So in the numerator here, we get 15 X is equal to X plus Y. So the larger one is equal to the larger one. Denominator, 6 and Y. So we're talking about the whole triangle and then the little triangle. The reason these are similar triangles is because they share the same angles. And so that's how we're able to make this assertion here. We know they share this angle because obviously it's the exact same angle. We know that these are both 90-degree these are both 90 degrees. And so then we can infer that these degrees are also the same. So they're proportional triangles, which is how we're able to make this equation, or this statement here, that they are proportional, that they are equal. And so from there, we're going to figure out how to get Y in terms of X so that we can plug back in for this Y and have it only in terms of X to take our derivative. So we cross multiply, we get 6X plus 6Y equals 15Y. Then 9Y equals 6X. Y is equal to 2/3 X. So there's a whole lot of setup work for this problem. And now we're finally getting to the calculus, and it's going to be smooth sailing from here. So we have figured out how to get this in terms of Y. To take a step back, that's why we did all this BS with the triangles to begin with this second triangle here, is because we're going to have to get this in terms of only X. And the way that the problem presented it to us, they didn't call it X and Y, but they gave us these two values as separate. And so, but then they asked us to find the rate at which those two values combined was changing, how fast the tip was moving away when they gave us that distance in terms of the distance of the person from the post and then the distance from the person to the tip of their shadow. So they broke it down into two and asked us to find the rate of change of them combined. And so then we have to, in turn, do some work to get the variables into a term and get our equation into terms of x's, because the only information we're given is this dx dt. And so since we found that Y is equal to 2/3 X, we're going to plug that in here. We get X plus 2/3 X, simplify that to 5/3 X. And then when we take the derivative, 5/3 dx dt, because we know that X is changing. And then we can just plug that in. And then our final answer is 25/3 feet per second. Any specific questions on this one?
Wait, so I thought, wouldn't 40 be X?
Excuse me. dx dt is what we're plugging in.
Oh, okay.
Mm-hmm. But yes.
So did we even need the 40 for anything? Was it kind of just there to confuse us then?
As soon as you asked me about the 40, my brain started thinking back on whether or not we used the 40. And so in general, I wouldn't say that it was thrown in there to confuse you. I wonder if there's another way to do this problem that uses the 40, but I did this problem myself and I was like, this is a whole lot I just thought it was really complicated. And so then I checked the textbook afterwards and the textbook did it the same way. But I wonder if there's maybe another way, possibly an even more complicated way that uses the 40, but you're right, the 40 is not used. This problem is a lot, guys. This is about as hard as it's going to get. Just to be clear, I would honestly expect easier than this on your exam. But still, to have you guys be well prepared, because I've seen these shadow problems before. I've actually seen them on exams before. Yeah, so there's a good chance you could have a problem like this. But based off of the conversation that I had with Dr. Zalecki during our meeting last week, I'm guessing it's going to be geared more towards spheres, possibly a rectangular problem. That being said, he did want you to be familiar with triangles and cones. And so we're going to get into cones really quickly here, sort of power through it. So like I said, I'm going to stop the share really quickly just so I can check and see. Oh, we've got some chat questions. If you have got individual questions, feel free to hang out afterwards, or if you can't hang out, you can email me. Why do you multiply by 5 at the end? 5/3 times 5. Tristan, I'm not sure what problem you're referring to for that one. Oh, I guess it's 12 or it's 241, so it's got to be this one. Oh, yeah.
Yeah, it's because the d8 over dt.
Yep. So 5/3 is these two combined. So we had x plus y, we plugged in terms of y. So then we had x plus 2/3 x, which combined gives us the 5/3, but we still haven't taken the derivative. We haven't dropped our differentiation symbolism. After we take the derivative, we're going to keep the constant, and then it's dx dt, and dx dt is equal to 5. So that's where that multiplication came from again. So let's get back to screen sharing, and we'll really quick bust through this conic problem. Again, if you got to get going, I totally understand. Water is leaking out of an inverted conical tank at a rate of 10,000 centimeters cubed per minute at the same time that water is being pumped into the tank at a constant rate. The tank has a height of 6 meters and the diameter of the top is 4 meters. If the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, find the rate at which the water is being pumped into the tank. First thing I want to address is that we're given mixed units here. We're given centimeters and we're given meters. We don't end up doing any conversions, although you totally can. And honestly, if I were doing this problem and for the first time and doing this on an exam, one of the first things I would do is I would get them all in either into centimeters or meters. However, for this problem, we don't do that because the units that are given in meters, we use those for special triangles, and they don't end up interacting per se with the units that are given in centimeters, because we're just going to use them in order to find the proportion. So backing up, we got our little diagram here. If I know that I'm going to be going through this way too fast, so if you need to, please be sure to go and check the recording, which I will post after recitation today. First piece of information that we're given is that, well, I mean, not the first, but we're told that water is being pumped in at a constant rate. The last thing they say is find the rate at which water is being pumped into the tank. So we'll come back to this in a second. The more concrete pieces of information that we're given is that dH dt, the rate at which the height of water is rising, is 20 centimeters per minute. Excuse me. And so this all relates to volume. And so we're going to have to use the volume of a cone equation. So the kicker about this problem is that so let's back up here. It says inverted conical tank is leaking at 10,000 centimeters per minute. So that's a negative rate of change. It's leaving the tank. But at the same time, we've got a constant rate of water coming in. And so our larger dV dt, the rate at which volume is changing, is going to be a combination of the water going in and the water going out. And so it's going to be C minus 10,000 centimeters cubed per minute. This is something that we come back to at the end. But what we need to focus on is dV dt. We need to focus on dV dt in the classic sense, where we're going to take the volume equation and we're going to crank it out like we normally do. It's all with most cone problems, you're going to have a similar triangle situation. And the similar triangles are like, if you'd like a visual, it's like that and like that. Those are the similar triangles. They share angles. And so we're able to say that they're proportional. And so we get r over 2 is equal to h over 6. I'm not going to explain too much about that. If you need to, go and look at the recording later. It's pretty self-explanatory, but I understand that if you don't necessarily have a wrap on it right away, because I'm breezing through this pretty quickly. And what we get from that is that r is equal to h over 3. And so now we can just go into the regular related, what we're used to seeing for related rates, and we can just take dv dt from this equation, having gotten this in a correct workable form for us, where we can plug in this h over 3, because we have h and we have r. But what we don't have is anything about the rate at which the radius is changing. We only have the rate at which the height is changing. And so we're going to use this relationship between the similar triangles in order to get them all into one variable, one workable form that works with the information that we're given. And so from there, we simplify to pi h cubed over 27. Now we do our differentiation. Once you get to the differentiation, you've done most of the work, and you can kind of relax. The setup is what's difficult about these problems. So dv dt, we're going to drop the 2, we're looking at this one here. We're going to drop the 3, and it becomes pi h squared over 27 times the rate of change of height, the height of the water, so times dh dt, which is going to be equal to, I just simplified that there. Then we plug in our values, 200, looks like I did do a conversion there. But either way, when we multiply that and we simplify it, we get 800,000 pi over 9. This is not our final answer. This is what dv dt is equal to. What we're asked to find is the rate of change at which the water is being pumped into the tank, which is that constant rate that was referred to in the beginning of the context of this problem. And so since we have set up this equation as dv dt is equal to c minus 10,000 centimeters per second, the rate in versus the rate out, we've just found the general rate of change as it relates to how quickly the height is changing. And so now we're going to plug in this information. And we know that dv dt is equal to this 800,000 pi over 9. We also know that dv dt is equal to c minus 10,000 centimeters cubed. And so we can get that c is equal to 800,000 pi over 9 plus 10,000 centimeters cubed per minute. Any questions?
Okay, so I kind of got confused up where it says the similar triangles. You did the r over 2 equals h over 6.
Mm-hmm.
Wouldn't it be like the 6 over 2 equals 2 over r?
I believe
Because
you'd
that's
get
what
the
they're.
same answer for that, wouldn't you?
Wait, I didn't catch what you said.
I believe you'd get the same answer. Well, 6 over 2 equals h over, yeah. So in terms of cross multiplication, you would get the same answer, but typically
Okay, yeah. I was just confused where the h came from, because on the diagram that you drew, there's only the
the number.
2 are in the r in the
Mhm.
6, yeah.
So I guess you're correct. I probably should have written that differently. For anyone who is just reading this and not listening to the explanation, that would probably also be confusing to them. But the part that I did touch on is that we're trying to get this all in terms of h, because we're given dh dt, but there's an r in here, which is why we're using the similar triangles situation in order to get it in terms of h coming from r. So we're doing the relationship between h and r, that proportionality.
Oh, okay.
Any other questions? We're about 8 minutes over recitation. That's totally fine with me, especially since we don't have office hours. So feel free to ask any questions, but
Hi, I have a question.
yeah.
Can you explain me how you took the derivative of the volume for the the volume?
This step here.
Yeah.
So we're taking it from this equation here. Did you follow that part?
Yes.
The simplified version there.
Oh, I get it. Yeah,
There you
yeah.
go. I see. I
Oh,
also
okay.
kind of got confused there for a second too. Yep. We're coming from the simplified version and then going from there. Yep.
Okay. And then also, if you don't mind, can you quickly show me the second part of the question 20, the last question that you did? That one. Yeah, so I can keep, yeah, sorry, I had to leave middle of the recitation.
No, that's okay. Yeah, go ahead. Is there any questions, or do you just need to look at it?
I just need to look at it.
Okay.
Yeah, I'm done. Thank you.
Oh, yeah, no problem.
Sorry, after she takes a photo on 25.
I'm done.
25. Yep. All
Yeah.
right.
Where did you get 200?
So that's a conversion. I did convert. I believe I did it from 200 centimeters. Wait, let's see. So this is dh dt. Yep. So I went from centimeters to meters, I believe. Yeah. That makes sense. Centi is 100. Wouldn't it be 2000? I've got the book right in front of me. Let's look. But this is this 200 is definitely a convert. Oh, it's from, is it from 2 meters or from 20 centimeters? I'm just there. I just went so fast that my brain is just kind of, it's like coming out my ears. So give me a second and we'll look. But I'm pretty sure that when I checked this in the book, I got this one right. Number 25 and 2.8. Anybody else have any other questions while I'm searching through the book? Okay. Yep. So the book doesn't specify the conversion, but h is equal to 200 centimeters. Yep. That's the height in this case, 200 centimeters. The height is 2 meters converted to 200 centimeters. That makes more sense.
Got it.
And then, so it's h squared, height squared times dHdt, and 2 is that, 2, where's the 2 from? Oh, yep, and then that one's converted.
2 is the DHDT
Yep,
converted to meter.
I believe so. Again, that's correct with, oh, that should be 20. That makes a lot more sense. This should be 20. No wonder I was confused, and you too. So this should be 20 because it's at 20 centimeters. And then we converted the 2 meters into centimeters. So this came from 2 meters. This is actually 2 meters, but then we converted it into centimeters. And then this 20 comes from the 20 centimeters per minute.
Okay.
Whew. Let me take a deep breath. I was talking so fast for so long. Okay, any other questions? I can't see who's still left in recitation, but does anybody have any?
I have one.
Okay.
So could you, over by the similar triangles where there's r over 2 and h over 6, could you quick explain, like I think someone kind of touched on this, like where if h is for height, why is that over 6?
So the radius, that's a good question, and now I'm confusing myself. I've still got the book in front of me. Page 2. So this is incorrect, is the reason why we're confused. So this 2 comes here from the radius, and then the h is the 6. So I shouldn't have written that in there, which is probably where the confusion started. But does that make sense now that I get rid of all that extra stuff?
Yeah,
2
okay.
goes to radius, and the h goes to 6.
Gotcha. Okay. Thank you.
Yeah, no problem.
Can you explain how dv dt of the volume function is? I understand how it's pi h cubed over 27, but then how does that turn to 3 times pi h squared over 27 times dh over dt?
Okay. Yeah. So first, so this is kind of that variable and then function situation. So first we're going to do the power rule on h. H is changing, so it's a function. We drop the 3, keep the 27 in the denominator, keep the pi because it's a constant, and h squared. Are you good so far on this power rule step?
Yes. Yes.
Okay. So since h is changing, now we're talking about basically what is the chain rule. Since h has its own rate of change, we're going to multiply this first aspect of the chain rule of the derivative by dh dt, because the rate of change of h is also going to contribute to the larger rate of change that is dv dt. Does that answer your question?
Yeah. You know how like implicit differentiation has like y prime? Is it something similar to like this, or?
Yes, that is so we're building off of implicit differentiation to do these related rate problems. It's absolutely a similar concept.
So since it contributes to the overall volume, you have to add it to it. You have to multiply to it.
Right. So since h, so if this wasn't h, if it was x squared, that's a bad example. But when you're doing the regular chain rule, if you see a part of a function that you could take the derivative of, again, you will do it. So if it's sine of x in parentheses squared, you're not just going to stop after dropping the 2 and reducing the 1. You're not just going to say the derivative is 2 sine of x. You also know that sine of x has a derivative. And that is going to change the general, the larger picture of the derivative. So you do the power rule first, you drop the 2, becomes 2 sine x. Then you multiply by cosine x. dH dt is cosine x in this case, because you know that h has a rate of change and that it's going to affect the larger rate of change.
For the like volume, like the same thing. If you're taking the derivative of like pi h cubed over 27, why didn't you do like quotient rule? Like you didn't do like 27 squared.
Well, you could do that, but 27 is not a function. So you could go through the motions, but you would just be giving yourself extra work. So it would be the derivative of the first times the second plus the first, or minus the first times the derivative of the second, and the derivative of the second would just be 0. So you'd cancel out that term and you just end up making yourself more work. Does that make sense?
So if like the bottom is like just a regular number, you don't have to take the derivative of it.
Yeah, so that's one way of thinking of it. Or you can also think of this in terms of pi over 27 being the constant. And then the
Oh.
function part is just h cubed.
Oh, got it. Okay.
Yeah, there you go.
There was another question I had. I don't remember what number it was, but it was like up a little.
Was it one of the related rates?
Yeah, it was something divided by 27. No, not the related rates. It was like the answer was something.
This one?
Yeah.
Okay.
So you did like -1/2 times 2. Wouldn't it just be -1? Or,
There's the 4 at the end here,
oh, okay.
which comes from the derivative of 4t.
Can you explain how you got like the 27 at the bottom?
Yes. Okay. So that goes back to the fractional power manipulations and everything. So we plugged in the 2 here. If you're good on the calculus, then we'll skip the explanation there. We
Yeah.
plugged in the 2, and then 4 times 2 plus 1 is equal to 9. So
Mhm.
this is where our jumping off point is as far as breaking down this fractional power. So if you remember what I said before about starting with the smaller powers and then doing the larger powers, because it's always, imagine like cubing 9 and then trying to take the square root of that. That'd be a very large number and a hard number to wrap your head around to take the square root of. So we're going to start with the square root first, which is, it's a square root because it's in the denominator. If it's the bottom of the fraction, it's going to make it smaller. If it's the top, if it's a numerator, it's going to make it larger. And so we're going to take the square root of 9 first. And in doing that, we can forget about the 2 because we've done the operation, right? These two are equivalent statements because we've taken the square root. But we still have this negative cubed to deal with. 3 cubed is 27. And that negative sign is going to invert it. It's going to make it an inverse, and it's going to pop it into the denominator. That make sense?
Yeah, that makes sense. Thank you.
Yeah, no problem.
There's this question on the review in the textbook that dealt with absolute value derivatives. Is that something you have to encounter, or is that something you have to worry about?
I did see in the true false, the question was, so as far as absolute value derivatives go, there's really not a whole lot that we have taught you guys. On the first exam, when we were talking about continuity and whether or not something was differentiable, we talked about it. So you should remember that. And by that, I mean, so if we've got an absolute value function that looks like this, technically f of 0 exists, right? And technically the limit from the left equals the limit from the right. So the limit exists at this point. It is continuous. However, we can't take the derivative because it's a sharp point. So that's really the large concept that you need to keep in your back pocket. For example, when we were talking, I remember when I was looking through the true and false problems, they asked whether it was like, if the function is continuous at a, then it is differentiable. This is an example, if a is equal to 0, of a function being continuous but not differentiable. So that would be probably the extent of what I would expect you to know for the exam as far as absolute value functions go. See if anybody's still here. We got a couple people. All right, any other questions? I do have to get going here soon.
This will be posted on the, this will be posted on the YouTube and the.
Yep. And you'll get an email copy of the recitation note as well.
Thank you so much.
Yeah, no problem.
You're gonna email us that copy tonight or tomorrow?
Oh, definitely tonight. I'm going to try and do it within the hour. Give you guys time to study.
All right.
And then what time? Oh, sorry.
No, you can go. You can go.
What time should we be on the Zoom tomorrow?
I
30,
think
right?
yeah, so as early as 7:15, if you'd like to ask questions ahead of time. I just have to double check the email. You know, I'm not the one studying for it. I just have to show up. So I don't know off the top of my head, but I
Okay.
think 7:30 is right.
Okay, thank you. And that's EDT, right?
Yeah.
Okay, thank you.
I had a couple individual questions, but I have class right now at 3.
Do you want to email me?
Yeah, I'll either email you, or since you're gonna send out the notes for this tonight, I might go to Dr. Z's office hours tomorrow and ask him.
Sure, whatever works.
All right, thank you. Because I feel like over email you don't get that like same description value. compared
Right.
to-
Yeah. I mean, if you can't get a hold of Dr. Zalecki, I'm not promising that I will be able to make this happen, but if there's a time that we could both meet and talk about a problem for 5 or 10 minutes, that'd be fine with me too.
All right, I'll email you. Thank you.
Yep, no problem, Keenan.
Have a nice day.
Yeah, you too.
Thank you. Have a great day.
Yeah, no problem, Caleb. Bye.